My name is HEIKO FESSENMAYR. I'm software architect at Agilent for lab and data communication standards. In the context of standardization organization, I'm Agilent's technical representative for the OPC Foundation and the Allotrope Foundation. I'm also the chairman of the OPC UA working group for standardizing analytical systems called ASI. Welcome to my presentation, Standardized Lab Data Integration based on OPC UA and Allotrope. This is about providing vendor-neutral analytical data for biopharma manufacturing and automated analytical workflows. So I will first give a short introduction into the analytical lab software layers and the related companion specs which are in the works. Then I will set the context and explain the use cases for this presentation today. And then we will go into the actual main topic, which is about bringing OPC UA and Allotrope together to build a standard for the analytical lab. First, a short introduction into the analytical lab software layers and the companion specs related to that. When you look at the analytical lab layers, there are basically four software layers and one hardware layer. At the very bottom, there is the analytical hardware. On top of that, you have the device drivers controlling the hardware, and the device drivers get integrated into an instrument system, which is again integrated into the data system. Finally, the data system is usually linked to a lab workflow application. This could be a LIMS, which stands for Lab Information Management System, an ELN, which stands for Electronic Lab Notebook, or an LES, a Lab Execution System. The workflow is the analytical sample is submitted. The data system starts the data acquisition and collects data. After the data has been acquired, it's processed and report is generated. And finally, the results and raw data is stored in a data storage. Then the consumer which triggered the analysis can read the results. So the chromatography data system is provided by a certain vendor which has its own developed instrument system and device drivers for their hardware. But other vendors' hardware has to be supported as well, and they have different device drivers for their hardware. So integrating other vendors' hardware and their device drivers into an own data system means significant effort, since the driver architectures are different in communication and data. And therefore, the goal of the Analytical Lab System Working Group is about standardizing the device driver level and their integration into the instrument system. This is currently what we are working on in the context of HEIKO. We are closely collaborating with the LADS OPC UA Joint Working Group to harmonize the standards. HEIKO is mainly targeted for the analytical data system and analytical hardware providers. But the end customer, usually out of the pharma or chemical domain, still face vendor-specific interfaces and data formats exposed by the different data systems. This is planned to be addressed by the ADSI OPC UA companion spec, which is also in the context of our working group. The working group is currently working on HEIKO. ADSI is planned for the future. So let's switch to the use cases. One use case is the automated analytical lab with its workflows. The other is integrating analytical data system for process control and monitoring. For the automated analytical lab workflows, a set of devices has to be linked together. Linking means interoperable communication and data format. Both are not standardized today, and therefore there's a significant integration effort needed to link such systems together. To reduce the integration effort, vendor-neutral data formats and interoperable communication between the various systems is needed. This could be achieved by OPC UA and Allotrope Foundation standards. Next use case is the online process monitoring. An example for this is biopharma manufacturing. The biopharma process control triggers sample taking from the bioreactor to see how far the process is. The sample is submitted to the liquid chromatography analyzer, and the data system is analyzing the sample. The analytical data system provides results back to the BioPharma process control. And again, at this point in time, this is not really standardized. There has been an OPC UA companion spec called ADI in the past, but this is basically outdated. Also, this could be solved by the afterwards presented concept combining OPC UA and Allotrope together. Let me explain briefly the current analytical lab standardization efforts and how we could bring the data formats and the communication together. The current efforts of standardized data formats and communication for the analytical lab are so far being worked out isolated from each other. While on the data format side, the Allotrope Foundation has worked out data models in two file formats. One file format is called ADF for archiving purposes. The other one is the JSON-based ASM, Allotrope Simple Model. This is for data reuse and ingestion into data lakes. Again, both are file formats, so one has to exchange files to get the information passed. On the communication side, there are OPC UA-based efforts, LADS and HEIKO. But these do not specify analytical data formats so far. Bringing both worlds together, that means exposing the Allotrope data as OPC UA Information Model would fill the current gap. How to realize this? ASM files are ideal for ingesting a complete set of data into data lakes. The consumer of the data has to pass the whole JSON data. In use cases we are looking at today, you do not need all the data, and a more direct access where OPC UA is the ideal solution is desired. That means the analytical data system produces and stores the results, and automatically or on request loads them into an OPC UA data server. One or multiple consumers can securely access the data. You might even use OPC UA file services to get the ASM file if really needed. Let me explain in a short sidetrack why OPC UA is ideal to address another need in this context. Here, a high-level overview of the data produced by liquid chromatography analysis. This comprises metadata of the measurements where JSON text format is ideal. But with each measurement, there's signal raw data produced. This binary data can be two-dimensional chromatograms and three-dimensional spectra. Especially three-dimensional data can become huge, and therefore it's not really ideal to be transported in the JSON text file format. Transporting this binary data with the OPC UA binary encoding is much more efficient. As a proof of concept, the Allotrope liquid chromatography data format was transferred into an OPC UA nodeset2 using an OPC UA modeling editor. Then I used the OPC UA model compiler to generate C# code for the opcua.net library. This code was integrated into an OPC UA data server, and the logic was added to load chromatography data into this address space. With this, it's possible to read liquid chromatography results in an allotrope way via OPC UA. So how would such a data fit into the LADS information model? You see here the structure of an LADS OPC UA server, and the Allotrope information would be placed into the results set folder as shown. Another opportunity that opens up by basing on OPC UA is easily exposing the same Allotrope information via a REST API. Adding an OPC UA REST API facade to such a data server immediately offers accessing Allotrope data via REST API with standardized data types. Let's switch to a short demo where I will show an OPC UA data server with that content. And this is being connected by an OPC UA client and also by an OPC UA REST gateway. Okay, so let's switch now to a short demo. You can see here an OPC data server with two connections. One is to the standard OPC UA client in the back, and then the other one is an OPC UA REST gateway. And when we switch to the standard OPC UA client, I have already prepared some data here. This has been loaded into this structure. And then you can see then the ones who are familiar with ASM will see that this is pretty similar to what is existing in ASM today. So you have the chromatograms information with the chromatogram values. You have the peaks, so with the well-known properties, peak area, peak height, retention time. And then other information like the data acquisition method name, the data processing method name, the injection information, like when it has been injection and what volume was used, the instrument system that was used to acquire the data, the sample name and the sample submitter, and also 3D UV spectra information is available that can read in a binary fashion here. And so this is a normal OPC UA client, so every OPC UA client can browse that infrastructure or this information model and can read information out of it, either a whole structure or just parts of it as it's needed. And then you can see here in the REST from the here browser that accesses the OPC UA REST API gateway server. You can see here the same structure that you can see on the left. And so there was no additional effort in the REST gateway to make this structure available. So you just link the OPC UA REST gateway to the OPC server, and then automatically it browses the content of the OPC server and exposes this via REST APIs. So that was what I wanted to show. What are the next steps? After last week's joint press release of the Allotrope Foundation and the OPC Foundation, the LADS joint working group will work on a proof of concept. And in the Allotrope chromatography working group, I will propose starting creating a draft for an OPC UA Node Set 2 that could be the base for a future companion specification. Thanks for attending this session, and if there are further questions, don't hesitate to contact me. Thank you.